Hi, I'm Stephanie Santosa with Meta's Reality Labs research, and today I'll be presenting our work on affordance-based and user-defined gestures for spatial tangible interaction. Mid-air hand gestures have been widely adopted by AR/VR products, but there are still key drawbacks to these interactions because they lack tangibility and tactile feedback. There's a quote by Hiroshi Ishii that really captures this sentiment, saying, "People have developed sophisticated skills for sensing and manipulating their physical environments. However, most of these skills are not employed in interaction with the digital world today." Bringing tangibility into spatial interfaces is an open challenge, especially if we want to build solutions that can be widely adopted for different environments. Tangible UIs have been explored in prior work for spatial interactions. However, much of this work requires custom hardware and is designed for specific tasks and contexts, rather than providing a more generalized solution to this problem. A promising direction is to leverage everyday objects in one's physical environment as opportunistic tangible user interfaces, which allows the user to take these objects and use them as proxies for input. In our work, we build on this towards a vision for an adaptive tangible user interface that can dynamically compose tangible UIs for you based on your current tasks and the existing affordances in your physical environment. We focus on two core research questions. One, what are the characteristics of tangible objects that impact their suitability for different types of input? We call these affordance factors, and we wanted to discover how they influenced the type of gestures that could be performed. Two, what are the desirable tangible user interface gestures for different input commands, and how can they be determined by their associated affordance factors and adapted across different objects? In exploring these questions, our research makes the following contributions. First is an elicitation study that we ran to understand what the appropriate gestures are for a range of physical objects and tasks. Second, based on this, is a user-defined object-based gesture set that can be applied to a range of 2D and 3D spatial interface tasks, which is illustrated here. Then, to determine the best objects to use with each gesture, we present an affordance-based object selector scheme. Arising from our findings is our vision of an adaptive tangible user interface, which supports the composition of tangible interfaces on the fly, based on the affordances found in the physical environment and the user's input task. Now let's start with the design for the elicitation study we ran to investigate our research questions. In our study, 22 participants with diverse professional backgrounds were shown desired effects to elicit various gesture inputs, and were asked to perform the gesture that they believed could cause the effect. For example, a participant could be shown a button being clicked, and then decide to tap on the surface of an object as the gesture that could cause it. We used the term reference for these desired effects, and there were a total of 12 referents over 6 scenes with 10 different objects, and we'll go over what these were later. Participants were initially shown the objects and then viewed all the scenes referents. They were then instructed to perform a gesture for each referent with every object. Participants used a think aloud protocol explaining the choices, and we had a Wizard of Oz setup which allowed them to observe the user interface effects of their gestures. Then at the end of each scene, participants selected the most desirable gesture for each referent. Here's some footage from the study so you can get a sense of how it was run. You can see participants performing various gestures to match with the referent effects that they were shown in this Wizard of Oz setup. We identified 12 referents across 6 interface scenes shown here. 4 scenes and 7 referents focused on 2D content, while 2 scenes and 5 referents involved 3D content. Referents vary from controlling a switch to more complex 3D manipulation, including one in a video game that involved performing 2 tasks, direction and acceleration, at the same time. This is the object set we included. As I mentioned earlier, we defined an affordance factor as a relevant characteristic of a tangible object that impacts its appropriateness for different types of input. To make the object set as scalable as possible, we selected a combination of objects that covered a wide range of possible affordance factors, which was determined from our review of prior taxonomies of shape-changing and tangible UIs. So here's how our object set covered the space, and this table shows geometric affordance factors like surface, size, curvature, edge length, as well as kinetic factors like being movable or elastic, and how we coded each object against the factors. Now let's go over the analysis and results. 43 hours of data were analyzed and labeled with a description of each gesture performed and its relevant object affordance factors. Gesture labels included name, hand usage, location, pressure, and relevance affordance factor based on Think Aloud audio. An example of this is, this desk has a big flat surface. I want to touch it like using a trackpad. Researchers performed open coding to categorize and group gestures and factors, and had high consensus, which indicated that the labeling was reliable. The first part of our analysis determined our user-defined gesture set for a spatial tangible interaction. In this analysis, we calculated the agreement rate for each referent and object combination to identify the level of consensus among participants' proposals. The mean agreement rate was 0.43, which indicates a high level of consensus, and consequently, this meant that a gesture set could be generated with a high level consensus among participants. The gesture proposals were categorized into types of gestures based on the hand and object movement involved. This illustrates our main set of 14 gestures that occurred more than 5% of the time for at least one referent. Once we had our gesture set, we can observe their distributions across referents, giving us the most appropriate gesture for each referent. This graph shows all referents except the flight simulator ones, which are in a similar graph that's separate that you can see in the paper. We highlight the most popular gesture for each referent with a solid outline, and this is what we classify as the primary gesture for it. We also identified the secondary gesture, which is shown with the dashed outline, since the most popular gesture may not always be afforded by the objects available. This can be used as an alternative in an adaptive system. For example, if we look at the first reference set, finger tap is the primary gesture for on and off, and movable structure input is the secondary. This provides us with an overall mapping between reference and gesture types. During the study, participants engaged in Think Aloud discussions, sharing object affordances that influenced their gestures. For example, a flat surface or a grabbable size. Video data analysis yielded 9 affordance factors based on the Think Aloud data. This figure shows these factors and how they are categorized. We found that certain factors align with the initial selection criteria, for example, size and curvature, while others, such as geometric shape of the entire object body, had no significant impact on the chosen gestures. In a similar manner to our other graph, where we map gestures to reference, we now map affordance factors to gestures. We identified the primary affordance factors and secondary affordance factors for each gesture type in our user-defined gesture set, which indicates the main properties of an object that afford each type of gesture. So looking at the first column, we see that for a finger tap, the primary affordance factor is a surface, and the secondary is a button-like feature. This gives us a sense of the association between gestures and affordance factors. Based on our analysis results, we created an Affordance-Based Object Selector Scheme to provide a framework for identifying suitable objects for each gesture type. For each gesture, we list the associated primary and secondary affordance factors and an example object. By developing this object selector scheme, our results can be generated to arbitrary objects by considering their associated affordance factors. Based on our findings, I'll now give an example for our vision of an adaptive tangible user interface. Tom is a designer who works in an automotive design studio. This morning, Tom receives a new design proposal from his colleague. Tom wants to check the one-to-one 3D hologram in his AR glasses, but it's hard to control such a large hologram with hand gestures. In this case, the potential input task is rotate the hologram. Based on our user-defined gesture set, the system identifies object rotation as the best gesture for this task. And based on the object selector scheme, the system identifies an easy-to-grab cup on the table as a suitable object to afford this gesture. The system renders an indicator on the paper cup. Tom double taps on the cup to activate it. Now the 3D object is attached to the cup. Tom holds the paper cup and rotates it, and the one-to-one hologram rotates with it. Now he wants to leave some comments. He grabs a marker on the desk. The system identifies the potential tasks are recasting and writing, and the sharp tip of the pen makes it perfect to afford those gestures. A sketch icon appears, and he double taps the button to make it a stylus. He uses this pen to select an area on the 3D car model, and he can now leave some comments just by handwriting with his pen. There are a number of core technical challenges to call out to get to a real version of the experience that I just showed. This type of system would require a way to detect objects and affordance factors, a UI that can be composed against user interaction goals, and adapted to nearby objects in real time, and of course, support for hand tracking and tangible UI gesture recognition. These are all complex challenges that go beyond the scope of our work here, and many different research areas would need to come together to realize the vision that we present. In conclusion, this paper presented a study of opportunistic tangible user interface gestures and affordance factors that led to a user-defined object-based gesture set and an affordance-based object selector scheme. This work provided a systematic understanding of the desirable object-based gestures for different input tasks in spatial computing, and the characteristics an object needs to afford those gestures. Arising from these findings is the vision of the adaptive tangible user interface, which supports the on-the-fly composition of tangible interfaces based on the user's input task and the affordances found in the physical environment. Thank you for listening, and please check out our paper.